ahead. This will have more. This one is more complex. So how we can apply that PCA on a complex data. So it's the same process that we have gone through. So you can see where we are slicing out the code, the headers that we need in order to remove all the identifiers, right? So that all our value can be numeric, right? Now, this is where we are framing it. This is where we are framing it, not just framing. This is where we are centralizing it. Remember that we have to, using that PCA concept, you have to get the center, you have to center the data. You have not forgotten. We have to center the data. So here we created an object. Okay, you have question? We did not center which one? This one. We center now. There's no way you go through PCA that you not center your data. It is not when you get the center that you now rule your line. You must center before you get your line. Either what is it called? Either perpendicular line or any other line. You must center. Is it not there? Yeah, there's no way you must center, but that center is the 0 point. Okay, so should we practicalize it, or let me just run through it and then go to TS niit? Should we go through it again? Should I allow you to apply the same concept? No, it will help you to deepen your understanding. But if we don't mind, we can just go to TS niit and continue. It's the same data. Or should I should go and do it as an assignment? Well, let's decide. Though it will not really take time. It will not really take time just for you to. This is where we stopped last time. This is where we stop. Yeah. Now, this is the beginning. This is where you are loading in that data again. Yeah. Right? Then this is where you are removing, you are extracting the headers that matters. And also dropping the identifiers. Then this is where we are transforming it. You can see the fit word underscore word transform. You still remember this process? Now, while we are transforming, we are also standardizing so that all the value can be between 0 and 1. Now here, this is where we are reducing from how many column? How many columns we have here? 1, 2, 3, 4. This is where we are reducing it to 2 components, since it's still PCA concept. Yeah, 2 is kind of more easier for you to arrive at reasonable interpretation. Now, this is where we are explaining. Remember, we talked about the variance ratio, right? Good. And then this is where this is the interpretation of that word variance. At the end of the day, we discovered that the PC1 higher protein and the lower is equal to sugar plus calories. So depending on that, then this is where we are transforming the original data into PCA. That we want to add the header. Then here, this is where we want to plot it. This is where we are plotting it. Then this is the continuation of everything could not enter one slide. So the code continue here. This is where you are showing the graph. And the next slide is the graph, showing you different clusters. And then this one there are names attached to the yes. Yes. Now this is, you can see it here now. We actually use more attributes in this one. You know, that one that we plotted, we did not define height, did you define width? No. So you can see that, I think as you, so there are so many attributes that I introduced here. which I think it will be good for you to use them so that you know. But if you don't mind, what I will do is that since we are going through it, I will drop the video recording with you guys so that maybe on your own you can go through it so that we can just go straight to TS.
So that we can do it.
Yes, so just take your time to do it. So let me just glance through so this is the assignment. Once you have done it, this is the assignment that will help you to understand the entire concept better, where you will interpret and visualize what the PCA. So you go through the assignment, and then this is the assignment solution. The assignment solution is there. And then you can see that the assignment, we are using a different data set. Is it the same data set? I think it's grade this time around. Student what? Grade, right? Where is it here?
Student grade, I think.
You have it now. You have it. Please confirm, because for you to be able to do that assignment, you will need the student grade. Okay, good. Okay, so this okay, so grade center. So this is where you are centering the data, and then so this is where you compress it to two column. This is where we want to frame it as data, and this is where you are adding the column description. Then this is where you are plotting it. This is the graph you end up getting, and then this is just like comparing feature selection and feature extraction. Because what we did now is feature extraction. Then this is where you visualize the assignment version, and then this is where we talk about the PCA next step. This is where I summarize some of the next step. Once you have fit and interpreted a PCA model, the next steps are data visualization. If you are able to distinguish data points visually, you are all set. If it is difficult to visually distinguish data points, you can vary the input, modify the number of dimension, etc. You can try other dimensionality reduction techniques, such as what? So it is something that usually leads towards considering this option, where something is not possible or easily performed with the PCA. Then you have this option. For me, I prefer this option because it's very straightforward, the TSN. So that is what we are trying to explain here, that where you are having some difficulties, then you can switch to to the other technique, which is what brought us to TSN now. So let's start with the TSN now properly. So this is where it starts. So TSN, what does that represent? It represents distributed stochastic neighbor embedding. The TSN represents distributed stochastic neighbor embedding. Is a non-linear dimensionality reduction technique. So at least with this, we have seen the differences now, right? The other one is linear, which is the PCA, where you have to rule a straight line to determine the cluster of data points. But in this context now, or in the case of TSN, it is not linear dimensionality reduction technique that emphasizes relationship between points. So the diagram we have on the screen has a little bit explain what it is. So this X here, so this one is talking about, now if you look at the keyword we should look at for us to easily understand this concept is the neighbor. So how easily, now we are looking at this X here. And now we are looking at this other data point and this other data point. So which one can easily become neighbor? Which one can easily associate with this S? That one is called the neighbor. Are you following? Now, TSNA is not concerned with maintaining the absolute distance. I think I should display it in a bigger. Are you seeing it? This is 67%. Let me put it on 100. Hope it's clearer now. Can you see better? Okay.
Yeah.
So TSNA is not concerned with maintaining the absolute distance between the points accurate. Instead, it focuses on offering a useful estimate of the relationship. So the key factor here is the relationship between data points. So that is what the TSA uses, the relationship between the data points. All right, so now let's quickly look at how it works. So this is just like the theoretical aspect of it in order to give us the background, how the different libraries within Python will be performing these clustering techniques, or a technique that will help us to determine the number of clusters. So how does it work? Number one, it calculates the distance between points in a high dimensional space. Number two, it uses the distance to calculate the affinity score between 0 and 1. The affinity here represents what? The relationship between for each point with the rest. In other words, how likely it is that they are neighbors. That is the statistics that is going to be performing. Then number three, it calculates the average affinity score for each pair of points. Then number four, randomly place the data point in a low dimensional space. The number five, use the affinity, that is the likely possibility of being attracted as a neighbor. That is for the data point. Uses the affinity scores between pairs to attract high affinity or repulse low affinity the points until they have stabilized into their final position. So that is the logic behind what this function TSA will be doing for us. Can I proceed? I'm not passing. Stay up on that set. What slides was that? Okay. It's like there's still one part here. Have you written this last part? So let's look at the example of the use cases. So to what benefits will you apply this technique? When you are or when you want to visualize your clusters in limited dimensions to spot check cluster segmentation output. So even the entire technique, both the PCA and the TSNE, they are both to enable us to know how many what clusters we can cluster our data into. So now let's look at the step 2, use the distance to calculate the affinity. All these are still the theoretical aspects in order to give us the background on how the entire function is going to perform at the end. So use the distance to calculate the affinity score between 0 to 1 for each point with the rest. So like I mentioned before, where you have high affinity score, that is what equals to high probability of being what? Neighbors. And if you look at the calculation here, so we are looking at the points, we are looking at each of these density from the X as the focal point. So we are looking at all these as data points. So we are just picking the data points randomly and seeing which one can be the direct neighbor. Now here, where you have AB, so here we are focusing on what? This side, AB, and then let's say after the calculation, we have a 1.5. And then the affinity of AB is what? Is high. Affinity of AB becoming what? The neighbor. Then we have distance what? ZQ, which is this. Remember that we are focusing on what? The S. So here we have 3.2. So the affinity of ZQ is also what? High. So how does this work? Based on the density of points around A and the distance between A and B, it is highly likely that what? B is what? A what? Neighbor. Then even though Q is further from Z than B is from what? It's from A. Since Z is part of a less dense region, there is still a high chance that Z is what? Sorry, Q is what? Z neighbor. So it's just a kind of illustration for us to have a background of what the function will be doing. So we are just picking different words, station, and different data points just to further explain the TSNE. Now here is still the same concept, but here now we are focusing on A and S, between A and what? S. And we have 5.3. So what is the affinity? It's low. The affinity is low. Now, to look at Z and X, that is Z and S, the same value. So, but our affinity is what? Medium. Now, why is the affinity here medium? because you can see that what, and this one is low. We're looking at the density. The dotted line surrounding it is what signify what? The density. So the density here is high than this. That is why it's not as low as what? As the affinity between the A and what? Because right now you are now using the density as a factor to know or to predict the neighbor, not the distance now. Then still the same thing. Here we are also picking on A and S, and then the same logic, try to show it in different locations. So here we have affinity AB. So we are looking at what? A and B, high, and then affinity Z. So we are just picking random stations to calculate or to assume their affinity. Okay, this one. Okay. So if you are curious, the affinity score is calculated by putting the distance through a Gaussian transformation and calculating probability. But it is not something you should be worried about. All right, so it's still the same illustration. So let's just go straight to where we have the practical to go through. All right, so finally at this point, we use the TSNE to reduce the visualization to 2 dimension based on the relationship between what? The data points. So here we are I'm trying to give us the summary of the differences, what we have been able to achieve so far, or in relating this TSNE with the PCA concepts. So PCA concept, which is the principal component analysis, it is a linear. Why here is what? Non-what? Linear techniques. So we just have to write this so that we can know the differences and know when to apply them. If yes, exactly. Yes, this particular note here. All right, so now let's go to our notebook and try to demonstrate the TSNE concepts. So the first thing we are going to do is to import the TSNE from sklearn. That is the first code. Now, this is the code for the visualization. This particular last one. So this is just like picturing all the code first before we start implementing them one after the other. So once we get to that aspect, we'll just be writing. So just capture this code first. The entire, here we are importing the TSN from sklearn, which is part of what you have written. Then here you are creating a TSN object and then storing your data components and the random states. And then here we are transforming and modeling the data. Here we are framing the data. And then here we are plotting it with a scatter plot. Okay. So application of TSN. So you have imported your library, sklearn. Dot manifold import TSN. Right? Then create TS object equals to TSN, the number of components, equals to 2. Specify the random states. States equals to 42.
What 100 you use?
Hmm?
I say what 100?
What the 100 I use? Let's go to the slide. This is the slide, the one I'm writing. They different from the one you.
The one eventually goes to 100.
From which slide did you copy it? Is it the previous one or this one? This is where we started from now. Have you? The application. And this is the first code you wrote. Have you?
Yes, we got this one.
Uh,
Yeah.
Which one have you? Okay,
Yeah,
here, right?
it.
Here. Okay. That's what you're talking about. Okay. Yeah, you can actually use anyone. You can use 42, you can use 100. The only thing is that what that particular attribute is doing is to determine how it will change each time you run it. That is the work of that random state. If we don't add it, it means that each time you execute the code, the value will change. But putting it means you are making it fixed. So let me just get to here first. Do I have data? Is it the same name of data I am using here? Let me run it and see if I'll get dot head. I hope I have this particular. Yeah. Okay, good. Thank God I have it here. So the next step, I don't know if you have written that. This is where we are transforming it to to two components. Have you written this one?
Okay.
Okay, so here, let's transform the data TST dot fit underscore transform. Supply the name of our data. Oh, it's not going to. Okay, so we have reduced the three column. How many column? 1, 2, 3 to what? To two components. That is what we have achieved here now. So the next thing is to frame it. Is to frame it because those values, they are just array. So for us to frame it, we have to use the data frame object or function. Have we written that before? Hope you are following. So let me just create a sub data where I want to save the transform copy. That's data TSNP equals to the TSNE. So what we are simply doing here, I think let me just copy that. Let me just copy this one because this one that we are just making an object before we can frame it. Control C. Then I'll just give it data object name, data underscore T S me equals to. So let me get this settled. Now to frame it, PD dot data frame, then I'm supplying these objects. Control C. Yeah. Okay, so I frame the data. Have we gotten to that place? Now let's add the column names so that we have descriptive headers. Okay, now to add the column name, add column name. All we need is just to update this code. Let me take this, Control C, paste. Then I will just add a comma, then all column attributes equals to, then select the headers. First one is component 1. component 1, comma, followed by component 2. Component 2. Okay. Just run it. So we have added the headers. Have you done that as well? Okay. So the next one, we want to plot the data. Let's plot the data. Since we have given it defined headers, now we can plot, because if you have not added the columns, you cannot plot it, because there will not be S representative and Y representative. So in this case, we can say S is for component 1, while Y is for component 2. So here now, plotting the graph, plot the data. So I will just say df underscore ts ni equals to copy the whole of this. Take the whole of this, Control C, paste it. So that is to create it and store it in an object. Now we will take the object, and I believe we must have imported or loaded Seaborn and save it as, I don't know if we have done that, but not.
In this.
Eh?
You used it in this. It's imported in this notebook already. Somewhere it was used.
Okay, that's what I want to confirm. Then scatter plots. Scatter plots. Scatter plots. And then define our axis. This is equals to, and then we say component 1. And then we use a comma. You can break it. Then Y is equals to component 2. And then supply the data. Data is equals to the data we created here. Just Control C. So let's add this to close. So let's check. Have you got to your graph?
Yes.
Name SN is not defined. Are you sure? Okay. Let me run again. So I have to import, let me import Seaborn somewhere. Say import Seaborn as SNS. How come I did not have it? People have said, okay.
The plots, the own graph, look at the difference.
Said your graph is different from our own. What is it different from our own, or just the same thing? Okay. Let me see your own. Your own and my own is the same thing. Yes, yes, it's only your own that is different.
The numbers there are not very unexpected.
Uh, Wait, this is what you implemented, right? Then this should be the outcome. What did you get? Let me see. Why is that? But it's almost the same thing. Mine and yours. The only thing is I don't have any cluster here. It's like you have about 2 data points. Let me see your own. Okay, and your own and my own, but just that the location of. Okay, I don't have anything here. Let me see. Let me see. So I have some cluster. Okay. Yeah, right?
No.
The graph. Okay, to go up. Okay. What do you have there?
Yours is minus 8 to 2.
Minus
minus 2 to 8.
I don't want to put it to
You don't have positive. Now, you remove the identifier, Abi. I think it's from the data. This very one is as if I was still working with the previous TS. This is where the issue is.
Yeah. If you put
it's plotting in.
Is fitting it into the.
Yeah, the other one that we have done, which is supposed to be this very one after removing the. Yes. So I think you guys, you are correct based on the data you are working.
It's going to be different from mine.
Our own, and it's the same data.
Same data.
Even the other one we ran, our own was a bit different now from the notebook, so cannot really judge it. Yes, that's the reaction. That's why it's not error. It's from your notebook, or maybe the intelligence in your Python. Yes, all these things are just statistical. May not be the same, exactly the same, based on your level of notebook intelligence. Now here, here we want to so here we want to also plot another type of graph entirely, and that is also involving. So here we create a plotly scatter plot with levers. So it's still the family of the scatter plot, because that we are using more attributes here, just like that other one that we skipped the other time. So I think we should. Yes, we should apply this. Yes, we should do this one because we skipped the other one. Is yeah, let me see. Yeah. This one you are creating another scatter plot. It's still part of scatter plot, but we are using a loop. You can see what we are bringing here now. So we are adding what? Loop. Adding data label using what? Annotation. Then for I, so this is loop. So you can just give it a label of maybe scatter plot 2. Scatter plot 2 because it's still scatter plot. So what we want to observe is the introduced attributes that are not in the first one. this time around. Is it the same? Let me see.
But in past, follows the what you have combined
Your own give you different.
as
Okay, okay, good. So this is the outcome of mine. I think it's similar now.
Yeah.
Okay. So this is an assignment you are going to take home. So let me confirm if you have this data first. Data that this is assignments. I think is which data is this? This is grade now. You have it now.
Yeah.
So you are using it for the assignment. So the key objective of the assignment is to reuse the TSNI model with two components. Plot the student on a scatter plot with the x-axis as component 1 and the y-axis as component 2. Then interpret the data you see on the plots. So this has officially brought us to, once we submit this assignment, officially brought us to the end of all supervised learning. So our next meeting will start with supervised learning. That is where, I told you that one does not have much work.
Yeah.
It's this one that have 80% of data cleaning. But there you just want to train the module to start passing in our data for predictive analysis. So those visualization commands that we have used so far, take your time to store them. But if you are working, most of those things can be derived from ChatGPT. You just substitute. You don't need to waste your time writing them. All those plenty visualization code, you can derive them from ChatGPT. Once you ask the question, you get there. You just know where to put your data and all of that.